Hi and welcome back to Never Trust an Atom. Today we're continuing with the Welcome to Space series and going back to astrobiology. What are we doing? Well, I'm going to introduce you to perhaps the second most famous equation in physics, the Drake equation. Essentially, it's a long list of variables that, upon finding the values, will tell us the number of intelligent, detectable alien civilizations in the galaxy. I'll go into more detail into what this jumble of letters actually means, but for now, let's take a look at how it came about. Like much of science, the equation gets its name from the guy who formulated it. Frank Drake is known as the father of SETI, both the field of science and the organisation. Back in the 60s, when radio astronomy was in its golden age and interest in space and aliens was at an all-time high, Frank Drake began to scan the skies for radio communications from two nearby sun-like stars, Tau Ceti and Epsilon Eridani. Unfortunately, he detected no such signals, and we've still not seen any, despite further lengthy and detailed observations being made. But it wasn't a complete waste of time, as both stars have been found to have planets and a debris disk. Even though the first experiment didn't find what he was looking for, it got people interested in the scientific search for aliens. So he set up a meeting, sometimes known as the Green Bank meeting, to discuss. But he needed a framework to guide the discussion, and thus the Drake equation was born. To this day, research groups at the SETI Institute can all be grouped under each of the variables. The first variable, r star, is the rate of star formation in the galaxy. This can be found crudely by dividing the number of stars in the galaxy by the age of the galaxy, which gives a value of about 10 stars a year. But this doesn't match up with the current estimate of star formation, which is measured by how many young stars there are in the galaxy. This is because the original calculation doesn't take into account the changing rate of star formation over a galaxy's lifetime, as a younger galaxy will have a much higher rate of star formation than an older one.
We can infer the rate of star formation and the age of the galaxy from its colour, as areas with high rates of star formation appear blue, as they make lots of high-mass, short-lived blue stars, versus in an older galaxy, only the long-lived red dwarfs are left.
A more accurate rate, using the young star survey method, is about 3 stars a year, which is a little bit higher than Drake's original estimate. Next is the fraction of stars that have planets. Drake originally suggested this to be about 20 to 50%, as at that point we hadn't yet discovered any exoplanets. But now, thanks to the Kepler Space Telescope and other methods of exoplanet detection, we know that exoplanets are actually really common. So far, we've discovered about 4,000 exoplanets, and there are thousands more yet to be confirmed. From this, scientists have estimated that nearly every star has at least one planet, and many have more. So a more up-to-date estimate of FP would be nearly 1. But not all of these exoplanets are capable of being home to life. Of the 4,000 discovered so far, over half of them are ice or gas giants like the outer solar system planets, and only 163 are anything like the inner rocky planets. Originally, the NE variable was the number of Earth-like planets per star with planets, but now we call it the number of planets that have a suitable environment for life per star with planets, for reasons that I'll get into later. The Green Bank meeting put this variable at between 3 and 5 habitable planets per planetary system, but the discovery of the prevalence of gas giants and exotic solar systems has cast that number into doubt. It's probably below 1. It's easier to consider the total number of habitable planets in the galaxy, which Kepler data puts at about 40 billion out of 100 billion stars. This puts FP times NE, which is just NE if FP is 1, at 0.4 planets per planetary system. Then the variables turn from astronomical to biological, with FL being the fraction of habitable planets on which life appears, which Drake put at 1, meaning that under any habitable conditions, life will always arise. which on one hand makes sense as life on Earth appeared to develop as soon as conditions became habitable, but it would also suggest that we should see many trees or many origins of life, as life should have developed many times on such a habitable planet like the Earth. However, if we find evidence of past or present life on potentially habitable worlds like Europa or Mars, then this would validate the claim that FL is closer to 1. Following from this, the next variable, Fi, is the fraction of those planets that develop life that go on to develop intelligent life. Now, this is one of the most controversial variables, as it depends on what you class as intelligent life. Some believe that if conditions remain habitable, then intelligent life is inevitable. But even under that assumption, Fi probably wouldn't be 1, as it took 3 billion years for single-celled life to evolve into just multicellular life, a further billion to evolve into animals, and another 600 million years to get to where we are today. So conditions would have to remain fairly stable for a long period of time. And looking at our solar system, where both Mars and Venus have lost their status of habitability, that's not always the case. Linked to intelligence, but put into its own variable by Drake, was the fraction of those intelligent civilisations that are capable of communicating by releasing a signal to space. This is very much a factor of its time, as back then the only method of detection would be by those radio waves that Drake worked with. Now, however, we have multiple different methods of detection potentially, such as biosignatures, so there is some debate over the importance of this variable. We as humans have only been in this category for about 100 years, which is a tiny proportion of the history of the Earth, let alone the universe. And as communications can only travel at the speed of light, the number of detectable species is limited. However, it's possible that civilizations could have developed earlier in time, so if they continue to survive, they will have been transmitting for a much longer period of time. How long they're able to transmit for is encompassed by the final variable L, the lifetime of an intelligent civilization. But there's so much uncertainty in this factor, partly because people argue over what a civilization is in the first place. Should each empire or dynasty count as a separate civilization, or is the entirety of the human race one civilization? Personally, I think the latter makes more sense. But what if we manage to colonize different planets or even different solar systems? There's a lot to think about. All of these variables combine to give N, the number of currently technologically advanced civilizations in the Milky Way. Although the astronomical variables can be and are being empirically measured, the huge uncertainties in the final biological variables have made some scientists look for a replacement to or an updated version of the Drake equation. Some of the proposed changes involve using the number of stars in the galaxy instead of the rate of star formation, taking into account the galactic habitable zone, or the expansion velocity of a spacefaring civilization. Alternatively, we can change what we're actually looking for. The current Drake equation tells us the number of transmitting civilizations today, but by throwing out the L variable altogether and combining a few of the other variables, you get a simplified or revised version that tells you the number of technologically advanced species over the history of the observable universe. Or you can get rid of the intelligence factor altogether and simply look for the number of planets with detectable signs of life by their biosignatures. This is known as the Seeger equation and is actually more useful given current knowledge and capabilities. Another thing to consider is what we regard as habitable. For a long time we thought that only Earth-like planets could be home to life. But as we've discovered more about the outer solar system and specifically the outer moons, we've realised that this approach is probably too narrow-minded. This will become more important if we ever find evidence for life on moons like Europa or Titan. Well, as I said, there is a lot of uncertainty in the variables, and we get answers ranging from just one, us, to 15 million. I don't think that we're ever going to find an exact answer to the equation, and really I don't think it matters. Instead, it can be used like its original purpose, as a guide. indicating what to look for and how to find the answers as we discuss and research astrobiology.
Thanks for watching. I hope you're enjoying this mini-series on astronomical equations. Comment below if you have any questions and drop any ideas for videos. See you next time and stay curious!